Hi, I'm just going to do a quick video on EZ isomerism and cis-trans isomerism and where they're different, when they're the same, and how to work them out. Because we've got a couple of emails from people over the weekend who were a little bit unsure. So we can see two molecules on the screen here, two dichloroethene molecules, but they're slightly different. So one has the chlorine groups both on the same side. On the left, you can see they're both above the molecule, and on the right, you can see one's above and one is below. Now, if this was a single bond between the carbons, that wouldn't matter because they would rotate and be constantly swapping positions anyway. But because they've got a double bond, that means they are stuck in the position that you can see there. So if you remember, double bonds restrict the rotation of the molecule. So in order to decide which one is E and which one is Z, we need to use the Cahn-Ingold-Prelog priority rules, which is a bit of a mouthful. So we tend to just call them the CIPS rules. It's Cahn-Ingold-Prelog rules. So let's have a look. Now it's all based on the atomic number of the groups. Well, not the groups, but the atoms in the groups. The importance of the difference, that will be apparent on the next slide. So each one, we want to go around and work out the atomic number for each thing bonded to the carbon. So first example on the left is relatively easy. We've got a 1 for each hydrogen, and then we've got a 17 for each of the chlorines. Once you've got the atomic numbers there, we want to decide which one the priority groups are. And the priority groups will be the ones with on each carbon with the highest atomic number. So on the carbon on the left, we've either got the chlorine at the top with atomic number of 17, or the hydrogen at the bottom with atomic number of 1. So the chlorine at the top here is the priority group. And then we do the same on the other carbon, and obviously they're the same atoms, so the chlorine will also be the priority group. So in that isomer, the priority groups are on the same side. Obviously, if we go over to the other one, it's the same numbers. So we've got 17 and 17 on the two chlorines, and a 1 and a 1 on the two hydrogens. And the priority groups are going to still be the chlorines. So the key thing here, they're on the opposite sides to each other. So once you've got your priority groups, we can then decide which one is E and which one is Z. So if you've got the priority groups on the same side, then you are dealing with the Z isomer. And if you've got them on the opposite sides, you are dealing with the E isomer. And in terms of naming, that just goes at the start of the name. So for that first one there, it's going to be Z. Sorry, start that again. Missed a key bit there. It's going to be Z 1, 2 dichloroethene. Okay. So look at another example. So got one here, a little bit more complicated. We need to do the same thing. So we're going to use our CIPS rules to apply the atomic number to the atoms and pick the priority group. So we can start on the right-hand side because that's relatively easy. We've got 1 for the hydrogen again and a 17 for the chlorine. So we can straight away say there the chlorine is the priority group. On the left, go to the 2 atoms that bonded to that carbon, and we've got a 6 here for that carbon, but we've also got a 6 here for that carbon. So we have to go atom by atom. The first atom doesn't give us a priority group. So what we need to do is then go out another bond from those atoms to try and break the tie. So we're basically looking for one group that has something that's bigger than the other. So if we look at the bottom on the methyl group, we've got 3 hydrogens that are all attached to there. So they've all got a value of 1. And then above, we've got 2 hydrogens, but then we've also got an oxygen, which is 8. 8 of the oxygen is bigger than any of the atomic numbers in the group below. So therefore, that is the priority group. Now, the common mistake people make is they just add up the mass of the group, so the total mass of the group attached, and use that. Now, sometimes that will work, but not always. Maybe have a look in a minute at some examples where that wouldn't work. But because the 2 priority groups are on the top here, this is therefore the Z isomer for that molecule. Okay. And we have another look at something where I think it's worth having another go at one of these. So let's have a look at another one. Maybe once I've drawn this, maybe pause it and have a go yourself. So let's go for an OH. An H2. There we go. All right. So what looks like quite a complicated molecule there. Let's go through it, and hopefully you'll find it's not actually too bad. Pause the video now, see if you can work out whether it's E or Z. So let's have a look. Right hand side I'll do first, much easier. So oxygen at the top there, atomic number of 8. Nitrogen at the bottom, atomic number of 7. So that means that priority group is the OH. If we go on to the left, so we got 6 and 6. So tied at the moment, and then we've got a 6 and a 7 there. So the nitrogen breaks the tie over the carbon. So this one is the priority group, and therefore this is the E isomer. Now, here's an example where it is important not to just add up the mass, because you can see that bromine at the top. If you're just adding up the mass and to pick the priority groups, this bromine is much bigger than anything else in the molecule and would make that top group the priority. But we never actually get to the point where we have to consider the bromine in that numbering. Okay. Let's have a little talk about cis and trans now, because there are 2 ways of naming isomers that are to do with double bonds. There's EZ and there's cis trans. Let's have a look at the difference. So we've got, these are extracts from the spec at the top. So cis trans isomerism is a special case of EZ isomerism in which 2 of the substituent groups attached to each carbon atom of the CC double bond group are the same. So we only have cis trans when each of the carbons has an identical group. So an example would be something like this. So you can see in that molecule there, both in this case they've got 2 identical groups, but both carbons have got hydrogen on, for instance. and both carbons have also got a methyl on. This would still work if we replaced that one with a Cl, for instance. That would still have cis trans because of the two hydrogens that are positioned there. Now, this is the key thing with cis trans. We're comparing the position of the identical groups. So the two examples here for this is butyene would be these two. So hopefully you remember with a cis isomer, your identical groups are on the same side of the double bond. So the one on the left is the cis isomer, and the one on the right is trans, where the identical groups are on the opposite side to each other. We can also work out the EZ isomerism. So if we look at this one on the left, we've got a 6 and a 1 and a 6 and a 1. So your two priority groups are on the top here, and that is therefore the Z isomer. And on the right, it's obviously the other way around. So you got the two CH3 groups on the opposite side to each other. So that is the E isomer. Now again, the other extract from the spec in the top right just helps you out a little bit with this. So E will always be trans and Z will always be cis when each carbon has a hydrogen on it. And that's because hydrogens are always going to be the lowest priority. So there's nothing that is going to be lower in priority than hydrogen. So the other groups attached will always take the highest priority, and you will always end up with this relationship here that cis and Z and trans and E will be partnered in those particular ones. Now you can only use this as a hard and fast rule when each carbon has a hydrogen. So if we have a look at some examples where this isn't going to be the case, just to get a feel for this. So it is important that you carefully read what type of naming they want. Do they want EZ? Do they want cis trans? Is it a bit more open? So let's have a look at one where so for instance here, let's go for this one here. So let's do the cis trans first because that is slightly easier. So cis trans here, we can see the two groups that are identical to each other. Here and here, and they are on the same side as each other. So this is the cis isomer because the two identical groups are on the same side. If we now do EZ, let's look at the priority groups. On the left-hand carbon, obviously the OH group has priority over the hydrogen because of the 8 atomic number on the oxygen. On the right, though, we've got 8 on the oxygen, but then we've got the 17 on the chlorine down here. So this time, we're comparing these two. So they're on the opposite sides to each other. So that means this is the E isomer. So it doesn't follow the thing in the spec, but that's because there isn't hydrogen on both of the carbons. There is a Marchem Guy video on this as well, so feel free to have a look at that, but hopefully that just helps a little bit. If you're unsure, practice some questions, and just send an email over to either your chemistry teacher, or feel free to send an email to myself if you want any clarification. Hope that helps.